So good morning everyone. So let us continue with the syllabus topics. So we stopped at the control part of multi-cycle data path. So before we get into the details of the control part, let me quickly summarize what happens in multi-cycle implementation. The first thing you need to understand that instruction of execution is broken down into different stages and each stage is executed in a single clock cycle. So these are the typical stages of execution: 1, 2, 3, 4, 5. So some instructions will require all the stages, some instructions may not require all the stages. So we need to be very clear on what are the stages required for a particular instruction. If you look at this table, instruction fetch is commonly happening for all the instruction: R-type, memory reference, branches and jumps. Then instruction decoding is also common for all instructions. Then the execution is dependent on the type of instruction. If it is an R-type, you do it in a particular style. For memory reference, you go ahead with target address computation, and for branches you need something else, and so on. So if you look at this table, you can clearly tell me what are the stage happening in a particular clock cycle. For example, given an R-type instruction, if I am asking you what is happening in the third clock cycle, you can tell me 1, 2, 3. In third clock cycle, I am finding the result of A OP B. So this is a kind of assignment. You can study what is this. Is not less than or equal to. This is an assignment used in Verilog. I hope you remember what kind of assignment this is. If you do not remember, you can go back and refer. Okay. There are two types of assignments, blocking and non-blocking. Study about that. So this is now wherever you find less than equal to, it is not less than equal to comparison. It is actually an assignment. Okay. So the question was, what happens for R-type instruction in the third clock cycle? Likewise, I can ask many questions, and this will be a major type of questions that you can expect in the next assessment from multi-cycle data path. So we'll see a simple question here itself before we go to the control. See, look at the program. Some instructions are given and the question is how many cycles will take to execute this code. So this is the context of the question is in multi-cycle implementation. If the question was asked in single cycle implementation, it is easy to answer because we know that every instruction takes one clock cycle. So 1, 2, 3, 4, 5. For 5 clock cycles will be required if the context was single cycle implementation, but that is not our context now. We are now talking about multi-cycle implementation. So load word, how many clock cycles will be taken? To answer that, you must go back to this table, look at the load word instruction. See, you will find that load word takes 1, 2, 3, 4, 5. 5 clock cycles it is taking. If it was branches, it will be taking only 1, 2 and 3. For jump also it will be taking 1, 2 and 3. So first load word itself takes 5 clock cycles. Second load word also takes 5 clock cycles. Likewise it goes. Okay. You can in your mind you can visualize what is happening in every clock cycle of load word, because load word consumes 5 clock cycle. What happens in each of those 5 cycle you need to visualize or make note in your book. First clock cycle of load word, say where does this address calculation is getting done. Okay, now the question is not that, what is going on in the 8th clock cycle. Okay. To answer this, we know that first 5 clock cycle is consumed by the first load word instruction. Next 6th clock cycle, instruction fetch of load word. 7th clock cycle, what will be 7th clock cycle? Decode and register fetch. Then execution of target address calculation will happen in the 8th clock. That is how we answer this question. So next question is, in what clock cycle does the actual addition of this takes place? 2 and 3, the actual addition of 2 and T2 and T3. That means they are asking in which clock cycle you are going to add these two. Okay, so that also can be found out because first 10 clock cycle will be consumed by this, and next BEQ how many clock cycle branches? 1, 2, 3, 3 clock cycles. So 13 clock cycles are consumed by up to this, and then maybe in 14th instruction fetch, 15th decode, and 16th it may be taken. So you can verify they have given a clock cycle here, and this will be the type of question that you are going to get in the assessment for multi-cycle implementation. So today I will also share some more slides on multi-cycle implementation. You might have received it already in your email. Go through all of them and have a clear idea about multi-cycle implementation, so that you will not have to study it again for the assessment. Let us be very clear right from here it is. So now next question is, how are we going to implement the control? There is control. Now coming back to the control. So you can implement it as a next finite state machine, that is current state. That is each clocks, you can view the individual stages as a state. So if you are in instruction fetch and you are in getting a clock cycle, you go to the next state. While you go to the next state, what is the next state after instruction fetch? Go back and refer the table. This is something which you must understand. Instruction fetch, it will have a set of control lines. You need to assert that. Next state is instruction decode and instruction register file fetch. So you were in instruction fetch state, completed it, and a clock cycle comes and you are moving to next state. What is that? It is instruction decode and register fetch. So during this instruction decode and register fetch, you need to set some control lines high. Okay, so that is going as output. So again, from the instruction decode or register fetch cycle, next clock cycle comes and you are going to the next state, which is ALU operation. Likewise, every clock cycle pushes you to the next stage, and when you move from next state, from current state to the next state, you have to set the control lines accordingly, so that the actual operations that you wish to happen in the next state are happening. So the fundamental idea is, if you want to happen some operations on the data path, you need to set the control lines right. Otherwise, those operations will not happen. Okay, you think in my, okay, next step, addition should happen. There is no magic that when you think something and that happens in the data path. If you want addition to happen in the next clock cycle, you must set the control line for addition as high. There is no other option. Okay, now this is very simple to understand. This is how it looks like. Okay, there is a single control unit who is outputting all the control lines by taking input and current state from the data path. Okay, now this diagram also has been explained earlier. So this is, you are in state 0. And a clock cycle came, when you were in state 0, these were the values of your control lines. So you must understand why these values are given. So to understand this, you can refer another slide set which I have given, go through that, and what decides the value of control lines in each state. Then a clock cycle comes, you are going to the next state. Here you set some control lines. From here to the next state you go depends on the opcode. Okay, so current state input comes and you are going to the next state. It is nothing but your automata in the, what is that subject? You have something of FLA or theory of computation. So you are in a state, input comes, based on the current state and the input you decide the next state. That's the same thing that's happening here. So totally, if you let's say you are in state 0, you are going to 1, then you may go to 2, 6, 8 or 9. Let's take that your instruction is load word, you are going to this state. From here you are going to this one and goes. So likewise you have got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 states are there. Am I correct? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 2 plus 4, 6, 10 states are there. So how many bits will be required to represent each state? You need 4 bits. So 4 bit states and inputs from the instruction will generate the output of this. So this is how it looks like. So you have a control logic. Its output will be the data path control line, and the input will be the opcode value from the register, and you have a state register, because when you are in current state, this will have the same value. Then your next state will happen. So the state to which you go depends on the current state and the input. That is why this is also fed back to the input, because the next state becomes the current state in the subsequent clock cycle. Hope you are able to follow what I am saying. See, you are in a current state and you go to next state and a clock cycle comes. So your next state right now becomes the current state for the subsequent clock cycle. So you have to understand that. Okay, so this is the control unit. How this can be implemented? So this can be implemented as a combinatorial logic circuit where we take the input and take the output and implement. So you have got opcode, and the logic will decide when to assert all these things. A dot here means you are ANDing. Okay, this is programmable logic array. You feed all the control lines, opcode, 6-bit opcode, and the select lines. Then you get the thing. Okay, so this could be implemented. This is known as a PLA implementation of the control. So states are there. Based on the state value and the opcode, you do a combinatorial logic operation and get all the control lines. Okay, PC write, etc. Hope you remember the meaning of each of control line. This should be very clear to you. Okay. So next is rather than computing the control lines for each and every instruction, why not we pre-compute it and save it in the memory inside the ROM? That is the next thing, that is known as ROM implementation. That is for each input of the next state and the opcode value. That is, these are the input. For each input, we store a particular word in the memory, so that you need not compute. Whenever this pattern of input computes, it's like a multiple, you are giving, see, I am checking whether you know multiplication or not. You can answer it in 2 ways. You learn the generic algorithm for multiplication, and whenever I am giving a number, you apply the algorithm and give me a result. Another option would be you keep a multiplication table with you. So whenever I am giving a number, you will just look into the table and tell me. So the first thing is the actual implementation of multiplication, where you multiply whenever I am giving you a number. And the second thing is like you are having a table. So whenever I am giving you 2 numbers, you go and search the table and get the value. So this is as simple as that. There is a read-only memory which will have so many lines. Each line will be the value of the control code. Okay, so this is how it is implemented. So we'll have, since how many inputs are there? We have got 10 inputs, 6 bits for the opcode and 4 bits for the state. So we must have 10 lines. 10 address lines should be there, because each 10 bits will result in a particular combination. Okay. So this is how ROM is implemented. We'll stop the lecture right here. Going into the details maybe happen in the next class. So you go through all the slides which I have sent and ask me if you have any doubts. Okay, you can also go ahead with this slide also and ask me any doubts. Explanation I will postpone to the next class. Okay, thank you.